Hello. So today we're going to be talking about the periodic table. Just like the electron configuration videos, I'm breaking the periodic table into three distinct videos, so we'll kind of dissect it part by part. So today we're going to talk about specifically how the elements are organized on the periodic table itself, history-wise, and just some distinct groupings and labels that you could put on some of the elements. So starting with the history of it, we already talked about this a little bit before. The first periodic table was created by Dmitry Mendeleev in 1869. He noticed that there was patterns of chemical and physical properties between elements, and that was based on how he set the elements up according to their atomic masses. He was able to identify that as atomic masses went up in a certain increment, a pattern of chemical and physical properties would occur. Based on this, he was able to leave blank spots within the periodic table with gaps in the patterns in suspect that he knew that there was other elements that they had not discovered yet at the time. And based off his research over just a little under 200 years, we've been able to identify and synthesize almost like 90 new elements, I believe. So his work kind of created the foundation for what modern chemistry is today. An English physicist, Henry Moseley, kind of expanded a little bit more on what Mendeleev had in his original periodic table. What he did is that he used X-rays to determine the atomic number, or the number of protons in the nucleus of each atom of an element that we had already discovered. And he noticed that as the atomic number went up, the chemical and physical properties would also create the same pattern. So he was able to identify the atomic number, the number of protons that determines the chemical and physical properties as well. So he was the first one to actually reintroduce the periodic table in a new version where he actually rearranged them according to atomic number, which we still use to this day. So the modern periodic table is organized into rows and columns according to increasing atomic number of elements, which you already really know. The rows are referred to as periods. They are based on the principal quantum numbers of 1 to 7, which we already briefly talked about in electron configuration. They can also be identified as series. The rare metals specifically are identified as series, lanthanide and actinide series. That's based on the properties that they hold. Most of the time, you're just going to hear me say rows or periods. When you go into advanced chemistry, when you start talking about lanthanide and actinide and what goes on in those rows, you may hear series a little bit more. Columns are referred to as groups, and they're typically labeled by Roman numerals and letters, so 1A, 2A, 2B, 3B, so on and so forth. They're also identified as families, and the reason why is because as families you share a common ancestry. The way we can think about it in regards to elements, families share common properties, and this is where the pattern of chemical and physical properties started to occur. So this is like a modern periodic table that you would see nowadays, a very common one. As you can tell, a lot of the new elements in this version have not been incorporated, so this whole row is actually here now. It's just this periodic table is a little bit older. But you see that you have the principal quantum numbers on the left-hand side, and then you have the group numbers up top across. And then, like I said, the lanthanide series and the actinide series, this is what is labeled for these rows. And just to tell, the star indicates that they get stuck in right here, and that plus indicates that they get stuck in right there. So in regards to electron configuration, it indicates where those rows actually are on the periodic table. So the groups of the periodic table are given names based on their individual properties. So as families, you kind of have to name the family, right? Family names. So group 1A are called alkali metals. Group 2 are called alkaline earth metals. They sound a little bit similar, but they're completely different, so don't get those confused. Groups 1B through 8B, are the transition metals. And then 3A through 6A is the post-transition metals. Since they're in large groups, there's not any particular names for each column. We just group those huge groups together and just call them one big family. There is a couple of other names that some scientists may call some of the groups in the post-transition elements, but IUPAC, which is the International Committee for announcing these things, have not verified those yet. So I'm not going to call them that. So just for the most part, transition metals are the big, huge D blocks in the middle. Post-transition metals are pretty much the first three columns on the right side of the transition metals. Group 7A is the halogens, so that's something very important. you may have heard of halogens, like in light bulbs for your car and stuff like that. And that's the reason why is because they use those elements to create light in the filaments and everything. And then group 8A, which you're already a little bit familiar with, is noble gases. But the thing is, the multiple groups that we've labeled individually can actually be broader described in other subgroups. So groups 1A through 8A are called representative elements. They're the most common elements that you're going to use and see and are seen on the planet Earth. Groups 1B through 8B is the transition elements, which that's that huge D block in the middle. And then the bottom two series are called the rare earth metals, which I've actually referred to a couple of times. So to kind of just break this down a little bit more visually, if you can't see helium, it is there on the top right-hand corner. I couldn't get the capture to not cut it out. But the alkali metals are the row right here. So the 1A, so hydrogen, lithium, sodium, potassium, they all share similar chemical and physical properties. Even though they're different sizes, have different numbers of protons, electrons, and stuff, based on the increments of those, in addition of those subatomic particles, it allows them to have similar chemical and physical properties. So hydrogen has 2 more than lithium, and then lithium has 8 less than sodium, and then sodium has 8 less than potassium. So you kind of see a pattern here of pretty much like 8 protons and electrons allows similar chemical and physical properties. Okay, so alkaline earth metals is the second column, so that's the 2A. Again, they all have the same chemical and physical properties. And then we get to the transition metals right in the middle there, that's the D blocks. And then this is the post-transition metals, so it's pretty much all 4 of those columns. Like I said, there are a couple of names that you may hear now and then from other scientists, but they're not actually verified by the international community. So for the most part, just consider these post-transitional elements. They don't have any specific family names for those columns. And then you have the halogens. So the halogens are fluorine, chlorine, bromine, iodine, acetine. And then you have noble gases. So that's helium, neon, argon, krypton, xenon, radon. And again, noble gases are inert. They do not want to react with anything. So they have complete, they don't need to share their electrons or lose electrons or anything like that. So you actually have to manipulate these atoms to get them to do anything, because just in the normal state, they won't do anything. They just kind of float around and do their own thing. So then we're getting into the broader groups I was talking about. So the left-hand side of the periodic table and then the whole right-hand block of the periodic table are called the representative elements. So these are the ones you're going to see most of the time in nature and everything like that. Transition elements are the transition metals. And then you have the rare earth metals, which is the lanthanide and actinide series. So the natural elements, their atomic number is 1 through 92. So they're found in nature, both pure or combined to other elements. It really depends on their reactivity. But they're most abundant elements in the universe. 76% of the universe is hydrogen. 23% of the universe is helium, and other elements is only 1%. So a majority of the universe is only gas. So nebulas and asteroid fields and stuff like that, anything that has like space dust is very, very little in composition of like actual like metals themselves. But hydrogen and helium, since they're gases and they occupy a lot of space, and hydrogen has high reactivity with other things and helium does not, it allows them to actually do their own thing, create pretty colors like nebulas and planetary nebulas and radiation through the sun and everything like that. So other elements, you know, they're found on planets, asteroids, and stars. So actually things that have mass and gravity that actually pull those metals in to a centralized location to actually be observed. The most abundant elements on the Earth's crust is oxygen, which it makes up almost 50% of the Earth's crust, which you wouldn't think, right? But it actually does. Silicon, 25.8%, aluminum, 7.5%, iron, 4.7%, calcium, 3.4%. And then others are 9.1. A lot of you guys are probably saying, well, where's carbon? Well, carbon's in there. Don't get me wrong. But carbon is actually kind of put through so many different things. So if you kind of take that out, carbon is, we're all carbon-based life forms. That's correct. And we have a majority of all organic base is carbon. But the thing is that, you know, the stuff that is organic is not a majority of the things, one, on planet Earth, and two, in the universe itself. But in Earth's crust, I mean, carbon life forms are there. I mean, there's some, but there's not a lot. So this is within the Earth's crust. Most abundant in Earth's atmosphere, nitrogen, which you would think there would be oxygen, but it actually isn't. Oxygen only makes up 21% of it. So nitrogen is actually a majority of the air that you may breathe in and out on the daily. Argon, noble gas, is about 1%, and then others only makes up 0.05%. So any other gas, carbon dioxide and everything, even though there is a huge like ozone problem, and you know the thing about global warming and stuff, the other gases only make up less than a percentage of what is in Earth's atmosphere. These three main ones are what actually you know, combines the other elements to make those gases, but the majority of those elements is what's found in the Earth's atmosphere. Okay, so transuranic elements is the atomic number is 93 and above. They are quite unstable. Elements 103 and above may only exist for nanoseconds at a time. That's because they're highly radioactive, and based on their electron and atomic configuration, they're not stable in the electrical sense, so they want to dissolve or break apart into smaller elements to become more stable as quickly as possible. So again, they're radioactive. They can typically be found attached to other transuranic elements or natural elements. It's because, you know, when it's by itself, it's not really stable. But if it breaks off and it finds another element that it can be stable with, then we can identify that and break it apart and, you know, purify it if need to and kind of examine it more one-on-one. But we do find a lot of transuranic elements attached to other things in regards to, like, location and concentration and stuff like that. To be found in the pure form, the elements have to be separated from their counterparts and recrystallize. And what that means is we break it apart, we dissolve it, get all the bad stuff out or the stuff that we don't need, and then we reform the elements on its own to try to purify it to where that substance, that little sample that we have, is just that particular element or compound if needed. So of all the other elements on the periodic table, the elements are separated into three broader groups. So even past representative elements and transuranic elements and rare earth metals are actually into even broader groups. So there are metals and nonmetals. So metals conduct electricity and heat. Nonmetals do not, or at least they're poor conductors. Metals are malleables, which means they can be rolled into sheets. Nonmetals are not. Luster, so they reflect light from metals. No luster for nonmetals. Ductile, it can be made into thin wire like copper wire and everything like that. Not ductile on the nonmetals. And tenacious, which means they want to resist stretching. So like if I take an iron bar, it's not going to want to do anything. Nonmetals are not that. And then nonmetals are typically brittle, so they're easily breakable. So as you can tell, metals and nonmetals have the exact opposite properties. Now, then we get to the third one, which is metalloids. They're like nonmetals, but with metal-like properties. So metalloids can be conductive, you know, like metals, depending on what it's attached to. They could be Bohr conductors, depending on what they are attached to. So the way we break this up is that the way I try to illustrate this is that the black squares are metalloids, and as you can tell, the metalloids follow this similar pattern of like a ladder down the periodic table. So in the post-transition elements, there is this kind of diagonal line of where elements meet both non-metal properties and metal properties, and so it depends on what they're attached to that allows them to be only reactive in certain ways or have certain chemical and physical properties. So they're actually kind of weird. But for the most part, the things I want you to really focus on is that a majority of the elements on the periodic table are considered metals. So this whole left-hand side of the periodic table, even the bottom two rows or two series here, are metals. The non-metals is pretty much everything from carbon over. Okay, so everything here are considered non-metals. So the gases that you would find, carbon's not considered a metal, nitrogen, oxygen, phosphorus, sulfur, so on and so forth. So if you have your periodic table, what I would recommend is if you want to try to create brackets or anything to help you remember which are nonmetals and metals and metalloids, this will become very, very important in the next unit when we talk about bonding. But for the most part, that's what I want you to get from. And just to illustrate the new elements that were recently discovered is this in green block here. So just be aware of that. So alkali metals, just kind of a basic rundown of their properties. They're very, very reactive. They're not found pure in nature based on the reactivity. Alkali metals are dangerous. They're probably the most dangerous elements on the periodic table. If you take pure sodium and you let it sit in air, it'll ignite with air and explode. I've played around with that. I've done where I've had to take solid sodium and quickly stick it into a solution, because if you let sodium just sit there in the air, it'll actually start to spark and jump around and kind of freak you out a little bit, especially when you're dealing with organic, highly flammable compounds. Violently reacts with water. What I highly recommend is, if you've never seen Mythbusters, seriously, after you watch this video, YouTube Mythbusters alkali metals bathtub, and then you'll see what happens when they drop different alkali metals into water and what actually happens. That stuff is real, and I may demonstrate a little bit with sodium or potassium in the classroom, but I will not be bringing in like cesium or rubidium or anything like that. They're very soft. You can actually cut pure sulfur, well, not sulfur, excuse me, pure sodium with like a butter knife. Like, it's really, really soft. So it doesn't take a lot to break that stuff apart. Very low melting points. That's because it's, how it's laid out atom-wise, and based on the reactivity, it wants to go into whatever phase it needs to actually react as quickly as possible. And very good conductors, because it wants to give their electrons very, very quickly, as many as away as possible. So that's one of the reasons that they're highly, highly reactive. Then the alkaline earth metals, they're pretty reactive if you compare them to the alkali metals. Not as reactive to alkali metals, but still pretty reactive. Can be found in pure form. So, you can find them. You can find just magnesium, like in strips. I'll probably have some in my classroom. But you can have some magnesium strips, and they'll sit there and they won't react with the air that quickly. So you can find them in their pure form. They are pretty reactive with water, though. You stick them in water, they'll start fizzing and jumping around and stuff. Maybe not cause a fire, but for the most part, they're pretty reactive. Easily tarnished, which means they can easily be oxidized by like air and stuff. So again, if you leave stuff out for too long of alkaline earth metals, they'll relatively quickly start forming different compounds and losing their luster and stuff like that. Halogens can be found in both their pure and combined form. So this is kind of the gases that you will find in nature. They're typically going to be attached, or you can find them in pure form too. You can find chlorine gas, you can find bromine gas, stuff like that. They're what's called polarizable. They're very big atoms in regards to their radius, or how the electrons spread out from the nucleus. So what they can do is they have the ability to actually shift their electrons over to one side to make that one side of the atom very, very negative, while the other side remains positive, and that helps them bond to particular elements. And if you want to dive further into that, feel free to come talk to me or take higher chemistry classes, because it's pretty fun. Very toxic in certain amounts, chlorine gas especially. You have chlorine gas that even if you breathe in a certain amount, it will kill a lot of cells in your lungs, and you could die and form chronic diseases, pulmonary diseases. I don't remember. I don't know the medical term, but very, very toxic. So there might be some reactions that we perform in class where you will form byproducts of these gases, and when you do that, you got to do it into hood, the fume hood, because we don't want those gases flowing around and people breathing them in, and so on and so forth. But very, very useful in synthesizing materials. They are very, very useful in what's developing called catalysts. They're what accelerates certain chemical reactions and allows them to actually happen a little bit quicker. But they're very, very useful in regards to that. Noble gases, they're inert, non-reactive, very, very stable because they don't want to react with anything. Can easily become plasma, like, for example, neon signs. You pass an electrical current through it. As long as it's all neon in there, it'll quickly flow their electrons and allow big, bright light to occur. So they're very easily to become plasmas. But besides that, that's all it is for this video. I know this video was a bit longer, but very, very important. Feel free if you have any questions, please come talk to me, email me. Otherwise, I will see you in the next video or see you in class. Bye.